Hi. So to pick up where we left off yesterday, now we're going to talk about some more probability problems. These ones have to do with cards, and then in a few minutes we'll get to geometric probability. Okay, so I put up here some background information on a deck of cards. One deck of cards has 52 cards altogether. There are 4 suits: diamonds, clubs, hearts, spades. And in each suit, there are 13 cards of each suit. So in each suit, there's an ace, there's 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Therefore, there are 4 aces in the whole deck, 4 twos in the whole deck, yada, yada, yada. Although I see I made a little error here. I'll put it in a little extra comma. We'll just erase that. Look at that. Okay. So, this actually has a really weird title. I think it's called combinatorics, but the word was so bizarre I just couldn't even bother to write it down. So, I found this pretty interesting because the probability of being dealt a particular hand of cards is something people might want to know. So here's an example. Find the probability of being dealt exactly 2 sevens in a 5-card hand. So exactly 2 sevens means just that, 2 sevens, so not 1 7, not 3 sevens, but just 2 sevens. Okay, so this requires multiple steps, and I tried to lay them out here for you to make it a little easier to figure out what that probability is. So there's a couple of things we need to find. The first one is the number of ways to get 2 sevens out of the total of 4 sevens. This is a situation where the order doesn't matter because a 7 of hearts and a 7 of spades, 7 of spades, 7 of hearts, that's the same thing. They don't need to be counted twice. So this is definitely an example of a combination versus a permutation. So number of ways to get 2 sevens out of 4 sevens. Well, if we have 4 total and we're choosing 2 of those 4 sevens. Okay, so that's the first part. We're just going to leave it like that for now because in the end we'll just type this in the calculator. Okay, so let's now come down to the next part. Number of ways to get 3 other cards that are not sevens from the other 48. So that would be 48. C3. Okay, so let's think about that. The other 3 cards can be any cards. They don't have to be in a particular order. That's why it's a combination. If they're not sevens, then we can only count from the other 48 cards. We can't use the 52 total. And, of course, we need 3 of them. So what are the number of ways to get this A, and this B? What are the number of ways to get A and B? This is back to the fundamental counting principle. If you want number of ways to get A, which is 4C2, and you want number of ways to get B, 48C3, then the number of ways to get A and B would be to multiply them together. So that's 4C2 times 48C3. And again, we're just going to leave it like that for now. We'll just worry about the actual numbers at the end. Okay, so this is what we want to get. This is what would be called the favorable outcomes, the number of favorable outcomes. So this is a combination of the sevens that I want and the other 3 cards that I'm going to get, even though I don't actually want them. Okay, number of ways to get a 5-card hand. This is where we calculate the total number of outcomes. So if we're talking about playing poker or whatever uses 5 cards in the game, the number of different hands I could get would be 52, because that's the number of cards in a deck, C5 for the 5-card hand. Okay, and we know that the probability of getting 2 7s, or the probability of anything, theoretically, is the number of favorable outcomes over the number of total outcomes. Well, we just found the number of favorable outcomes. That's 4C2 times 48C3. And the total number of outcomes is 52C5. So this is a method you can use probably to find any combination of cards, any probability of whatever hand of cards you want to get. So now we're going to put this in the calculator. So if you remember, and I can show you this during our live meeting tomorrow, if you forget how to do this on your calculator. So if you forget, you could just leave it like this for now, and then I could go and tell you how to do that again. But it's under the math menu, and then you go over to prob and you choose NCR. If you have an older calculator, however, you will have to I can't type and I clearly can't multitask. If you have an older calculator, you need to type the N number first before going and getting the NCR button. But again, I can show you that tomorrow because I can show you the calculator on the computer through Teams, but I can't do it through my iPad, which is how I'm recording this now. So 4C2 times 48C3 is 103,776. And 50, excuse me. Oh, I never actually calculated this. 52C5 is probably some ridiculous number, but let's see what it is. Oh, all right. It's only mildly ridiculous. 259,896. You could certainly type this all in one step. There shouldn't be any problem with doing it that way either. And then we get 0.0399. Oh yeah, there we go. Okay. Which equals about 4%. So not a very good chance, I think. Okay, so now let's come down here. I have another one for you. It's a very similar type problem. So I really want to see if you can follow the steps from above and see if you can do this yourself. So I'm actually going to wait a minute and see if you can make it through this. So I'm just going to let the time tick away while you try this problem. Find the probability of being dealt exactly 3/8 in a 5-card hand. Okay, so hopefully you got somewhere, and if you're not ready yet, of course you can just pause the video. I don't know why I didn't think of that in the first place. So the first thing we're going to do is we're going to find the number of ways that you can get 3 out of the total 4/8. Okay, so that's going to be 4C3. Okay, let's come down to part B. Now we're going to find the number of ways you can get the other 3 cards. I'm sorry, the other 2 cards. Now remember, we're already getting, I'm sorry, I lost my train of thought. No, we need to get the two other cards because we're getting 3 8s in step A, right? So how many cards are there left that are not 8s? Well, just like in the previous problem, 48. So that's going to be 48C2, though, because I only need to get 2 more cards. Because I'm getting 3 up here and 2 down here. Okay, then if you remember, the next step is to put A and B together. So 4C3 times 48C2. And then step D is the total number of outcomes in a 5-card hand. We already figured that one out from the one before, too. Okay, 52C5. So then we basically take step C, divide it by step D, and you should be good. So while you're watching the video and taking notes, if you have questions or there's something that you don't understand, please jot down the question. You could jot down, you know, the part of the notes that you didn't understand. You could do it right on the notes. You could write down the time of the video that didn't make any sense, so that we can discuss it when we actually meet. Well, you know, it's all virtual, but so I'm just trying to figure out what this value is in my calculator. And you know me, I can't multitask, so that's not going very well. All right, let's see here. So I got 0.0017, which if you were to convert that to a percent, that would be 0.17%. So as you can see, compared to the previous problem, it's a lot less likely for you to get 3 of a number than only a pair of the number. Okay, so now another one for you to try. Find the probability of getting 4 7s in a 5-card hand. So first, we're going to get the number of ways you can get 4 out of 4 7s. So to get all of the 7s, that's going to be 4C4, which if you type that in the calculator, you're going to find that that's 1, because there's only one way you can get all the 4s, right? Oh my goodness, I keep typing this in wrong. There we go. 4C4. Yeah, is 1. I just need to double check. Okay. Part B, what's the way you can get the other card? Oh, hang on. Let's write down. We're not writing down enough of what we're doing here. So this is number of ways to get all 4 7s. Is it 7s? Yeah, 7s. B. So how many more cards do we need for the 5-card hand? We only need 1 other card. So this is going to be number of ways to get 1 other card. There are 48 cards left, though, remember, because the 5th card can't be a 7. So that's going to be 48C1. And that's going to be 48, I believe. Part C is to put A and B together. So the probability of getting all 4 7s and another card is going to be 4C4 times 48C1. D is the number of ways to get 5 cards, but we've already done that twice now. So that's 52C5. And then finally, take step C and step D and make a fraction out of them. And that is very, very small. 0.0000. Is that right? Yeah, 185. There is not a very good chance that in one deal you're going to get 4 of the same cards. That's for sure. Okay, so hopefully that gives you a little insight on how to find probability when dealing with a deck of cards. And last, we have geometric probability. You probably did this in geometry, but you also just might not remember. So we're going to find the geometric probability, in this particular case, of landing in this green shaded area. So if we were to take a randomly chosen point from this purple rectangle, what are the chances that I would land in the green section? This example is modified from your book, and it has to do with a strike zone of a pitcher, like hitting the high inside or something, but I could barely hang on to the sports behind it, so I just drew you the picture. Okay, so geometric probability is, let's fill this in here, because I see I did not fill that in, is the favorable area, or whatever they're, we call it favorable, but it's really like whatever they're asking you for. So in this case, they're asking you about the green shaded area, so that's the favorable area. Even if in baseball it's actually bad. And divided by the total area. Okay, so we're going to find the probability of throwing a ball and hitting this green area here. So the favorable area. Oh, this isn't going to work. I can't see the picture. Okay, there we go. So the favorable area, this is the area of a rectangle. So that's just going to be length times width. So 6 times 4, 24, right? The total area is the area of this entire purple rectangle that includes the green area and the other stuff. And that will be 17 by 22. So let's see what 17 times 22 is. It is 374. Oops, that's not where I wanted that. 374. So then the probability of the green shaded area is 24 over 374. And as a decimal, that's 0.0642. Of course, that's assuming that the pitcher will throw a ball that will land in this purple box, which I think was supposed to be the strike zone, and that he lands in just that little tiny green area. And it's kind of saying that the pitcher's throwing randomly in the strike zone, which, if you're getting paid like millions of dollars a year to play professional baseball, like I hope you're more accurate than just randomly in the strike zone, but maybe that's not actually how it works. So I hope you've not fallen asleep while watching my video, and I hope I'm still making you giggle every now and then. Try the rest of the homework problems for section 2, and I'll see you tomorrow to answer any